Okay, and welcome back. This is chapter 11, problem 6. So let's get started. This is a two-part problem. First part asks, what voltage will accelerate electrons to a speed given by 6 times 10 to the minus 7 meters per second? So let's just take a look at that. So, sort of hidden in this problem is, well, what we want to find is the work done because we're talking about accelerating the electron to a certain speed. So if we know the final speed, then we might want to consider the work done, because the work kinetic energy theorem tells us that this is equal to the change in the kinetic energy. And we also know that we want the voltage, so the work done can also be equal to minus the change in the potential energy. So this is the essential equation that we want to start with. Essentially, this is energy conservation. So sort of hidden in this problem is the fact that we want to accelerate electrons to a certain speed, which it seems safe to assume that we were starting with 0 meters per second as the speed. That is 0 kinetic energy. So what we have is that the work done is equal to just 1/2 the mass of our particle, which is the mass of the electron, which we can actually just look up, times the velocity of that particle squared. That's the change in kinetic energy part, because the initial kinetic energy is 0. The other way to compute this is, of course, through the change in potential energy, which is negative the change in the potential energy, which is minus the charge of the particle, which is the electron, times the potential difference. So just note that the charge of the electron is negative, so this is minus 1.6 times 10 to the minus 19 coulombs, so that the work done here is a positive number. Just there is no inconsistency. Don't be worried by the minus signs. We might also write this as being equal to negative the absolute value of the electron, like this, or just negative E. With the negative, we might say that it assumes that there's a negative sign embedded in there. So now we want to sort of put this together, because the two ways of computing the work must agree with each other. So you have that 1/2 mv squared, this is the mass of the electron, is equal to E times the change in the voltage. And we want to solve for that. So this is not too bad. We just divide by the absolute value of the charge, and we get that delta V is equal to mass of the electron times the velocity squared, divided by 2 times E. This is the symbolic version. So now let's also write down what this is numerically. So the mass of the electron, you can look it up. This is 9.1 times 10 to the minus 31 kg. Then we've got 6 times 10 to the minus 7 meters per second. And we square that. And this is divided by 2 times the absolute value of the charge, which is 1.6 times 10 to the minus 19 coulombs. You put all of these things together, you get that the change in potential is 1.02 times 10 to the negative 24 volts. This is an alternative version of the same answer that Jesse got. I went with this way without going through the notion of an electron volt, just because I think it adds a little bit of diversity. But just for completeness, 1 electron volt is the energy gained by an electron when a 1 volt potential difference is applied. So that is the charge of that electron, which is 1.6 times 10 to the minus 19 coulombs, times 1 volt. That's what 1 electron volt is. So one way to, so that is to say more compactly, 1 electron volt is 1.6 times 10 to the minus 19 joules. And so that's a useful conversion to know, because it's more proportional to the scale of what an electron experiences. It's just a change of units that's more appropriate for some of these problems. Now, part B, actually, let's scroll up to see what that said, and that says, find the radius of curvature of the path of an electron accelerated through this potential in a 0.5 Tesla field. So sort of the embedded assumption here, when you're talking about the radius of curvature, if you're talking about a radius, then this implies you're talking about a circular motion. Okay, and so you've got a particle which, depending on, so if it's originally going something like this, depending on if it's a positive or negatively charged particle, it will either turn one way or turn another way, so that the acceleration will be pointed in different directions depending on the charge. But in either case, so you can actually just deal with the absolute value, because the actual radius that's created by this will not depend on the sign of the charge. Essentially, what I mean by this is, if you've got circular motion, you've got a centripetal acceleration, which means that you've got an equation that looks like mv squared over r is equal to the force that's being applied, and that's going to be the charge times the magnitude of the velocity times the B field. And this equation works equally well for if this was a positively charged or if it was a negatively charged, because as you can see here, if it was negatively charged, then say like so, then the acceleration would also be in that direction. But if it was positively charged, then the acceleration would be in the opposite direction to that. So those opposites end up canceling out. So you don't have to worry about that. So maybe most of you would have just dropped the negative sign anyway, but that's why you can do it. It doesn't end up making a difference. So we have this equation, and we want to solve this for r, the radius. So what we're going to do is, if we want to get r by itself, let's do the easy thing. Let's divide by v on both sides, because there is a v on both, common to both sides. So we've got mv, I'll just drop the e subscript for right now, divided by r is equal to e times b. Now we want to get r by itself, so we essentially can just flip these equations upside down, but I'm just going to show you how that's done. Multiply by r on both sides, you get mv is equal to e b times r. Now divide by whatever multiplies r to get it by itself. Divide by e times b, and you get r is equal to mv, that's the momentum of the particle, divided by e times b. Perfect. So now we have all of these parameters. Actually, we know exactly what all of these are. So we have that the radius is equal to 9.1 times 10 to the minus 31 kilograms. We know the velocity is 6 times 10 to the minus 7 meters per second. we're going to divide by 1.6 times 10 to the minus 19 coulombs, and B is 0.5 Tesla. You put all that together, you get that the radius is going to be so that is a 6.8 times 10 to the minus 18 meters. Okay, so that's how you do problem number 6. If you have any questions, leave a comment in the comment section or send me an email. You know where to do it. Okay, have a great day.